Okay guys, let's get started. So today we're going to talk about the last part of validation. So if you recall, in the previous two lectures, we talked about the way we can use validation in order to select a model. And we discussed about the complexity of the model complexity of using a validation set. And at the end we found a dilemma that no matter what size we choose for k, we're going to run up into a problem that this inequality that was a generalization of Hoeffding's inequality will run into some issues. First of all, if we take a small validation set, or the k becomes small, so t1, this value becomes small, and also on the other side, t2 becomes large because this is on the denominator we have a small value. On the other side, we thought if we take k as a large value, the inverted situation happens, and then we're going to run into some issues as well. So the idea was to find a way to estimate the real out of sample error for the final model through a validation set. So we saw that in either cases, k being small or k being large, we're gonna run into some issues. So the way we try to alleviate the problem is by doing cross validation, and that's what we discussed previous lecture. So we said that this is the dilemma. We want to make sure that we cross-validate to avoid this dilemma. All right. So one of the variants of cross-validation is called the leave one out cross-validation. So just like what the name resembles, is in each of the test case, when you want to train your model and validate it, you leave one of the samples or one of the ends out of your big D dataset. So you leave one of them out, you train with the rest, and you validate with those. And you can repeat this in a loop, because you can leave every individual N out of your D, right? So if you want to make it more formal, as a definition, we say we partition D into training set of size n-1, and because one of those was taken out, so after we partition D into training set of d-1 size, we do the validation set on the size k1, right? So that was a whole D. We took this out. So this becomes val, the rest is going to be train, right? And that was the whole n size. And we can repeat this. So as you can see, intuitively there are n ways of doing this thing, because at each of the n step you can leave one of the k equal to 1 out of the n, so n becomes n-1. And you can repeat this n times. All right? So if you want to define it in a pseudocode, so we say for n from 1 up to, so the small n from n equal to 1 up to capital N, the training set will be this. So that was your previous training set D. Now we have D small n, which consists of x1, y1, x2, y2, up to x capital N, yn. However, xn, yn, the small letter n, has been taken out. So that was the element that was left out of the D, right? And we use this. So it's like left out. I use this in order to validate that dn, right? And you repeat this n times. At each of the points, you're going to take one of them out and then train with the rest. Okay, so now you see that when we train, instead of using d, we use dn, and we use this on with our learning algorithm. This will yield g minus n function, the hypothesis, the candidate in your hypothesis, and you test it with xn, yn, right? So this is going to be your validation set. And using this validation set, this will yield the pointwise error of that validation set on this gn, right, function. So the error would be e of g minus n, xn, and yn. So just like before, in any other validation technique that we saw, we assume that so we assume that En is an unbiased estimate, right? That was what we discussed 2 lectures ago. So it should be unbiased because it's coming from a uniform distribution. It's an IID. So we assume that En is unbiased estimate of the real test error. Thus, we want to make sure this holds. So the expected value of En, right, is going to be the Ex of n, and this will be this that we saw here. So the Exn of En, we hope that it becomes the real test error, right? So let's see if this holds. All right. So, as you knew, the cross-validation error, or ECV, is going to be equal to the average of all the pointwise errors, right? One by one. So E1 up to En, depending on the number of Ks you had. How did you partition your D, right? So the ECV is equal to the 1 over n of all those E's. Thus, the ED of ECV, the expected value of ECV, would be, again, 1 over n of the previous value. So you have n times repeated, because you're doing cross-validation n times, right? So you have to divide this, sum it up, and then normalize it by n. So this value, That's why you have a summation over n and divided by n, right? The expected value of d and the pointwise error of each of those individual elements. So now, this would be equal to have 1 over n summation of n's from 1 up to n ed, right? Edn because of that, and then you have the rest here. And finally, you have this value, which was equal to the test error E out of Gn, right? And 1 over n of the summation of all of these, the expected values, becomes the E out on average, right? This is the bar on that. So we're going to have E out bar of n minus 1 because you have calculated the error for n minus 1. And we say on average E out of n is equal to expected value of d E out G bar, right? I'm sorry, G minus. So we see that the cross-validation error resembles the same value. Actually it's an unbiased estimate of the test error. However, there are points to be considered. So first of all, how does the variance play about here, right? So the cross-validation error, or ECV, we mentioned that it's an unbiased estimate of E bar out n minus 1, right? However, the errors, each of the ENs are not independent, right? It depends on which point we choose. We're going to have another error. So suppose you have like a constant hypothesis, so G1, and also a linear hypothesis, G2, right? It depends now which point we leave out, or each point was left out when we compute the error, right? So the error here is smaller, and then it's going to be bigger, it's going to be bigger and bigger. However, in this case, if you pick a constant one, you're going to have the smaller errors, right? Less variance. So now we know that depending on the hypothesis, if it's linear, if it's constant, if it's polynomial, you have your errors, your ENs are not independent, right? So the variance in ECV is not equal to the variance of each of those divided by n, because they might not have the same variance. And one could be bigger than the other one, right? And it depends on the type of hypothesis we choose. However, in practice, we see that the variance is sufficiently small so that ECV sort of estimates the real E out. You know, it's reasonably accurate. But you see, if you cherry pick just like that above, you saw you have different variance depending on the different hypotheses, because your points are having different ENs, each of them. And they are not independent. All right. So one of the other variants of cross-validation is called V-fold cross-validation, or sometimes they say K-fold. But here, since we use K as the size of validation set, we call it by V here. You might see in some textbooks that they call it K-fold cross-validation. And the reason behind this type of cross-validation was, if you recall, the vanilla case of cross-validation was you have to do it n times, because at each of the steps you would leave one of the k's out of the d, and then you had to repeat it. So it's at some point it becomes a computationally intensive task, right? It has high computation cost for us. So in order to have us, have a bound on the computation, we want to make sure that we run it not just all the n times, but a lower number than that, right? So, and that was the idea of using the V-fold or K-fold cross-validation, is to limit the number of iterations we do by partitioning the D in a larger size, right? So that was the normal case. So you have to do it n minus 1 times multiple the computation of the training. So at each of those steps you have to train your model and then repeat. However, one of the ways to circumvent the issue, the computation here, is to do it V times. And that's why we call it V-fold or K-fold cross-validation. So given V, in this case, we split it into V equal size set. In practice, in many cases, you see on the papers they use 10, but I mean, this V can vary. So that was your normal grand, let's say, data set. So you partition them into V partitions. That was the overall size was n. So each of those D's are having n divided by n size, right? So if you pick 10, each of them, depending on the number of n, you have divided the n by 10, right? Each of them are 10% of the real data set, for instance. And this is a very popular technique to do. All right. So the algorithm goes as follows. So for m from 1 up to your V number, so we let the dm of training set, right, as all your training set minus that dm itself. So dm was left out. That's why we call it dm train, because it has all the d's excluding dm, and you use that dm in order to train a model, right? So the one left out was dm itself. So you use the train to train that, and you evaluate the em based on that. So you're going to have 1 over, in this case, instead of using all the n's, you have to use n, 1 divided by n, divided by v actually, right? And it's a summation of xn, yn over inside the dm set, and you have to compute each of those e's, the target and the estimates, the actual one and the estimate value, right? And finally, if you use this cross-validation, this V-fold cross-validation, the ECV, the error of your cross-validation, would be 1 over V, instead of 1 over n. The summation of m's from 1 to v en. Oh, em actually. So that's going to be the estimate of the E out. Okay. So let's talk about choosing a model when we use cross-validation. So this was what I exemplified some slides ago. So you see that we have a linear hypothesis called G1 here in blue, right? And we selected 3 points in order to evaluate the ease. So you see we have a variant error sizes, right? E1, E2, and E3 on these 3 points, X1, X2, and X3, right? The error involved in this cross-validation was 1 over 3 of the summation of ease, right? Which is a fairly high number. You can see that, for instance, in the case of E3 or E1, you have fairly high values, right? So without doing the cross-validation, we might have thought it's a linear hypothesis. So in previous examples, in the previous chapter, we talked about this. We might have even picked linear model, right? If you were just using the better fitting, right? However, if you use cross-validation, because the errors are not independent, suppose another case here. So you have a G2 as a constant hypothesis, right? So now you see that your error is much lower than the previous one. So now using cross-validation, by leaving each of those out and training on the rest, we see that the constant model is preferred now because it has lower value of error. Okay, so at the end, what matters for us in using cross-validation is the error on the outstanding points, right? in each of those fields. So the constant model, the one that you saw in the previous slide, so we had G1 is a constant, has a lower E out, and so cross-validation selected the correct model. Because right, that was your 3 points. 2, next one. And just like as you thought, CV is very similar to an estimate of the in-sample error, because at the end of the day, you're using your samples taken out of, so that was your samples or your training set taken out of your X, right? Instead of all samples outside. So you do folding or you do leave one out. At the end of the day, it's a very nice estimate. It's a close estimate of your in-sample error by doing cross-validation, right? Okay, any questions so far? I wanted to start the new and the final chapter of the course, which are SVMs, but I thought let's start it fresh on Wednesday. We're gonna be talking about those probably 4 lectures, and then yeah, your course will be over. Yeah, so on Wednesday, Friday, next Monday, and next Wednesday, we're gonna finish SVMs. Yeah, and that will be all for this course. All right, so see you guys on Wednesday.